And now in this lecture we'll answer two questions. In the first question, we find out the area of this circle that is described by this trapezoid ABCD. And in the second question, we find out the length of this line segment QB that is equal to x. So we start with the first question. In the drawing, we have trapezoid ABCD that is described that blocks this circle. Oh, the circle is inscribed by this trapezoid ABCD. A trapezoid is a quadrilateral with one pair of parallel sides. In this trapezoid ABCD, side AD is parallel to side BC. In addition, we know that this is line segment AM that is equal to A units in its length. This is line segment MB that is equal to B units in its length. Again, our mission is to find out the area of this circle that is described by the trapezoid ABCD. So first of all, we define the center of this circle. This point is point O. And we define the point of tendency of tangent AD with this circle. This point is point P. Likewise, we define the point of tendency of this tangent BC with this circle. This point is point Q. Here we can implement all two and quick on all two. According to all two, the lengths of two tangents for a common external point per circle are equal. So in the drawing we have a circle, and this is the common external point P. From this common external point P, we have two tangents for this circle, tangent PA and tangent PB. And according to this rule, all two are equal to each other. That is to say, PA equals to PB. So we can actually implement rule 2 in our drawing. Why? Because in our drawing, if we focus on this common external point A, from this common external point A, we have two tangents to this circle, tangent AM and tangent AP. According to rule 2, they are equal to each other. That is to say, AM equals to AP. So if AM equals to A, therefore AP must be also equal to A units in its length. Likewise, we focus on this common external point B. For this common external point B, we have two tangents to this circle, tangent BM and tangent BQ. And according to rule 2, they are equal to each other. That is to say, BM equals to BQ. But MB equals to B units in its length according to what is given in the question. Therefore, BQ must be also equal to B units in its length. So writing down, this is tangent BQ that is equal to B units in its length. In the next step, we join points O and Q together by a straight line. Point O is the center of the circle, point Q is the point of the circle itself, therefore OQ is the radius of this circle. We define the radius of this circle as x, so OQ equals to x, according to our definition, and because of the fact that the radius OQ is equal to x, the radius OQ is on to point Q, that is the point of tendency of tangent BC. If this circle, whenever your radius is drawn to the point of tendency, then tangent BC will be perpendicular to the radius QO. If BC is perpendicular to QO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we join points O and P together by a straight line. OP is of course the radius of this circle is equal to x, and because of the fact that the radius OP is equal to x, the radius OP is 1 to point P, that is the point of tendency of tangent AD with this circle. Whenever your radius is 1 to the point of tendency, then tangent AD will be perpendicular to the radius PO. If AD is perpendicular to PO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. In the next step, we will do a construction. That is to say, from this point A, we will go perpendicular on BC. Again, from point A, we will go perpendicular on BC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the starting point for the perpendicular from point A and BC. This point is point N. When doing this construction, we created those two angles. So we mentioned before, in trapezoid ABCD, side AD is parallel to side BC. So we have those two angles. Those two angles are defined as one-sided interangles and are located between the parallel lines AD and BC. And therefore the sum of those two angles must be equal to 180 degrees according to rule 17. So repeat quickly on rule 17. According to rule 17, the sum of one-sided interangles that are located between two parallel lines is equal to 180 degrees. So in the drawing, we have line A that is parallel to line B. The red line C intersects with those two parallel sides, those two parallel lines AB and those 2 points. In addition, we have those two angles alpha and beta. Those two angles alpha and beta are defined as one-sided interangles. And because of the fact that those angles alpha and beta are located between the parallel lines A and B, the sum of those two angles is equal to 180 degrees. That is to say, alpha plus beta is equal to 180 degrees. So we can actually implement rule 17 in our drawing. In our drawing, we have those two angles that are defined as one-sided interangles and are located between the parallel lines AD and BC. Therefore, according to rule 17, the sum of those two one-sided interangles is equal to 180 degrees. But this angle equals to 90 degrees. So 90 degrees plus the size of this missing angle, in total, the sum of those two angles must be equal to 180 degrees. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we will do another construction. That is to say, from this point O, we will go perpendicular on AN. Again, from point O, we will go perpendicular on AN. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point O and AN. This point is point T. By doing this construction, we created the small quadrilateral APON. Inside this small quadrilateral APON, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 4 piece angle, in total they must be equal to 360 degrees according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore this 4 piece angle must be equal to 90 degrees in its size. Likewise, inside this lower quadrilateral TOQN, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 4 piece angle, in total it must be equal to 360 degrees. Therefore, this 4 piece angle must be equal to 90 degrees in its size. So if we found out that the size of the big angle POQ is equal to 90 degrees plus 90 degrees, that is 180 degrees. So I write it down. the big angle POQ is equal to 180 degrees in its side, and we know that any angle that is equal to 180 degrees in its size, it is a straight line. Therefore, line segment POQ is a straight line. If POQ is a straight line, then PQ is also a straight line. And shape APQN, this shape APQN consists of 4 sides. 1, 2, 3, 4. So the long shape APQN consists of 4 sides. Therefore, shape APQN is a quadrilateral. Shape APQN is a quadrilateral because it consists of 4 sides. Quadrilateral APQN consists of 4 right angles, and we know that according to rule 5, any quadrilateral that has 4 right angles must be this rectangle if not a square. So we know to this quadrilateral APQN is a rectangle because it has 4 right angles. So write it down. This quadrilateral APQN is a rectangle according to rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So rectangle APQN, side AP must be equal to the opposite side QN. But AP is 8, therefore QN must be also equal to A units in its length. Likewise, according to the same rule, in the same rectangle APQN, side PQ must be equal to the opposite side AN. But PQ is x plus x, that is 2x. Therefore, AN must be also equal to 2x units in its length. So, this is side AN. This is equal to 2x units in its length. What is the length of the missing line segment 97 BN? BN equals to BQ minus NQ. So, I write it down. BN in total equals to BQ minus NQ. So BN in total equals to BQ is B, according to rule 2, minus NQ is A. So in total, BN equals to B minus A units in its length. BN equals to B minus A. Side AB equals to A plus B. So in the next step, I'll copy the right triangle ABN in the new page and we will implement the Pythagoras theorem on this right triangle, triangle ABN. This right triangle ABN. So according to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse AB equals to A plus B units in its length. Side BN equals to B minus A units in its length. And side AN equals to 2x. Here by PT is a permission for Pythagoras theorem. So actually, this is right triangle ABN, this is according to the original norm. This right triangle ABN, according to the Pythagoras theorem, AB squared, that is the square of the hypotenuse, equals to AN squared plus BN squared. So analytic norm, AD squared, that is the square of the hypotenuse, is equal to AN squared plus BN squared. AB is A plus B, therefore AB squared is A plus B squared, and it is equal to AN squared. AN is 2x, therefore AN squared is 4x squared plus BN squared. BN is B minus A, therefore BN squared is B minus A squared. So in total, according to the Pythagoras theorem, I should find out that A plus B squared equals to 4x squared plus B minus A squared. So we will open the brackets on both sides of this equation, and we get that A plus B squared equals to A squared plus B squared plus 2 times A times B, and this is equal to 4x squared plus B minus A squared. B minus A squared equals to B squared plus A squared minus 2 times A times B. So here we have A squared on both sides of this equation, so A squared gets cancelled, and we also have B squared on both sides of the equation, so B squared also gets cancelled. After we cancel those two expressions, this side of the equation we have only with 2AB, that's equal to, in the other side of the equation we have 4x squared minus 2AB. So here we add 2AB to this equation, and you get that 2AB plus 2AB is 4AB. So 4AB equals to 4x squared. And again, if we found out that AB equals to 4x squared, here we divide this equation by 4, and you get that AB, 4AB over 4 is AB, so AB equals to 4x squared over 4 is x squared, so x squared equals to AB. Our mission is to find out the area of this circle that is described by this trapezoid ABCD. Actually, we know that the area of any circle is equal to pi times the radius of the circle squared. Because again, the area of any circle equals to pi times the radius of the circle squared. And therefore, the area of our circle, the area of this circle must be equal to pi times the radius of this circle squared. So it is pi times the radius of this circle squared. The radius of this circle is x, therefore the radius squared is x squared. So in total, the area of this circle must be equal to pi x squared. But we just right now found out that x squared equals to AB, so we subtract x squared, we substitute x squared here by AB, and we get that this expression equals to pi a squared is pi AB. So in total, we found out that the area of the circle that we are looking for is equal to pi times AB square units. That is the answer to the question. Repeat again, if we found out that the area of this circle equals to pi times AB square units. We finish with the first question. In the next step, I present to you the second question, and I call the second question of this lecture. Our mission in the second question is to find out the length of this line segment QB that is equal to x. So in the drawing we have a semicircle. The length of AB is 30 units. Actually, the diameter of this semicircle that is AB is equal to 30 units in its length. In addition, you know that this is line segment AP that is equal to, or chord AP that is equal to 10 units in its length. This is chord PQ that is also equal to 10 units in its length. Actually, this is chord QB, or line segment QB, and it is equal to x units in its length. And our mission is to find out the length of chord QB is equal to x units. So we have to find out the value of x. So in the first step, we define the center of this circle. This point is point O. We know that the diameter of this semicircle is equal to 30 units in its length. If the diameter is 30, the radius of this semicircle must be equal to half of it. That is to say, the radius must be equal to 30 over 2, that is 15. The radius of this semicircle equals to 15 units in its length. Point O is the center of the semicircle. Point A is the point on the semicircle itself. Therefore, OA is the radius of this semicircle that is equal to 15 units in its length. Likewise, OB is also the radius of this semicircle that is equal to 15. In the next step, we join points P and O together by side line. Point O is the center of the semicircle, point P is the point on the semicircle itself, therefore OP is the radius of this semicircle that is equal to 15 units in its length. In the next step, we complete this semicircle to a circle. And we'll extend the radius PO by side line until it touches the circle. And we define the touching point of the external radius PO with this circle. This point is point M. The next step we join points B and M together by side line. Those two angles now defined as vertex angles, so we know that vertex angles are equal to each other. So if this is an angle, if the size of this angle is theta, then the size of this angle must be also equal to theta because they are equal to each other. Vertex angles are equal to each other. So in the next step, we'll prove that triangle AOP can go into this triangle MOB. Moving on, we prove that triangle AOP convert to triangle MOB. So why those two triangles convert to each other? First of all, side PO of triangle AOP is equal to side OM of triangle OMB. They are both the radius of the circle, therefore they are equal to each other. Each side is equal to 15 units in itself. OM is also the radius of the circle, which is 15. So side OP equals to side OM. They are both the radius of the circle is equal to 15 units in itself, therefore they are equal to each other. Repeat again, if we found out that side OP of triangle AOP is equal to side OM of triangle MOB. They are both the radius of the circle is equal to 15 units in itself, therefore they are equal to each other. In addition, those two angles are defined as vertex angles. We know that vertex angles are equal to each other. So actually this is angle AOP. In triangle AOP, and it is equal to this angle, that is actually angle MOB. In triangle MOB, they are equal to each other according to the rule that vertex angles are equal to each other. And finally, side AO of triangle AOP is equal to side OB of triangle OMB. They are both the radius of the circle is equal to 15 units in itself, therefore they are equal to each other. So it is known side AO of triangle AOP is equal to side OM, so side OB of triangle MOB. The both the radius of the circle is equal to 15, therefore they are equal to each other. So if you know that AO equals to OB equals to 15 units in itself, so we found out that those two triangles can go into each other according to side angle side rule. That is to say, those two sides and the angle that is included between those two sides in triangle AOP are correspondingly equal to those two sides and the angle that is included between those two sides in triangle OMB. Therefore, those two triangles can go into each other according to angle side rule. So I write it down. Okay, found out that triangle AOP convert, this is the sign of convert, to triangle MOB. According to angle side rule. And from the fact that those two triangles can go into each other, we derive that side AP in triangle AOP is equal to side MB in triangle MOB. So AP equals to MB according to the rule that corresponding sides in congruent triangles are equal to each other. Those two triangles congruent to each other, therefore the two corresponding sides AP and MB must be also equal to each other. But AP equals to 10 units in its length according to what is given in this expression. So you can write here that AP equals to 10, and for this expression 10 equals to AP equals to MB. We derive that MB is also equal to 10 units in its length. Okay, this is side MB is equal to 10 units in its length. This is called PM that passes through point O, that is the center of this circle, and you know that any chord that passes through the center of the circle must be the diameter of the circle. So PM is the diameter of the circle and also the diameter of this semicircle. So I'll copy this semicircle with the diameter PM and we will analyze this semicircle. Okay, this is the semicircle with the diameter PM that I copied from the original drawing. This inside this semicircle, line segment PQ is equal to line segment MB. You can say also that chord PQ equals to chord MB in its length. So point O is the center of this semicircle. So in the next step, we will extend line segment PQ and line segment MB by straight line until they intersect with each other. Hopefully this is the intersection point or the touching point of the extended line segment PQ with the extended line segment MB. So we define the touching point or the intersection point. This point is point E. By doing this construction, we can do triangle PEM. This is triangle PEM. Actually, we have the rule that if we extend two line segments that are equal to each other in their lengths, then the new line segments that you created must be also equal to each other in their lengths. Here, line segment PQ is equal to line segment MB, it is equal to 10 units in its length. When we extended those two line segments that are equal to each other in their lengths, the result is PE and ME. So the new line segment PE and ME must be also equal to each other in their lengths. according to the rule that I mentioned, PE must be also equal to ME. Again, when you extend two line segments that are equal to each other in their lengths, the new line segment that you created must be also equal to each other in their lengths. In this case, the new line segments are PE and ME, they must be also equal to each other in their lengths. So PE equals to EM or ME. So in triangle PEM, side PE is equal to side EM. And therefore this is an isosceles triangle. We know that those two angles are equal to each other in an isosceles triangle because PM is the base, or we can say also, according to the rule, that in front of equal sides in the triangle, there are equal angles. So in front of this side EP, we have this angle PME, and in front of this side EM, we have this angle that is actually angle MPE. And because of the fact that those two angles are located between in front of those two equal sides, they must be also equal to each other in their sizes. So if the size of this angle is beta, then the size of this angle must be also equal to beta, according to the rule that I mentioned. Okay. In the next step, we'll complete this semicircle to a circle. So in the drawing, we have quadrilateral PQBM. This is quadrilateral PQBM that is described by this circle. And we have the rule. So I'll write the new rule. If a quadrilateral is described by a circle, then the sum of its two opposite angles is equal to 180 degrees. So this is quadrilateral ABCD that is described by this circle. Quadrilateral ABCD has four angles, alpha 1, beta, and 2. Those two angles, alpha and beta, are defined as opposite angles, and according to this rule, because of the fact that quadrilateral ABCD is described by this circle, the sum of its two opposite angles must be equal to 180 degrees. So those are the two opposite angles, alpha and beta, and according to this rule, the sum of those two angles must be equal to 180 degrees. That is to say, alpha plus beta must be equal to 180 degrees. We can actually implement the new rule in our drawing. Why? Because in our drawing, we have quadrilateral QBPM that is described by this circle, and according to the new rule, the sum of those two opposite angles must be equal to 180 degrees. This angle equals to beta degrees in its size. So beta plus the size of this angle, in total the sum of those two angles must be equal to 180 degrees according to the new rule that I read to you. So beta plus this missing angle, in total they must be equal to 180 degrees. So this missing angle must be equal to 180 degrees minus beta. Why? Because 180 degrees minus beta plus beta is 180 degrees. That is the sum of the sum of the opposite angles in a quadrilateral that is described by a circle. Therefore, this angle must be equal to 180 degrees minus beta. Likewise, the sum of those two angles must be also equal to 180 degrees. This is angle beta plus this missing angle, in total must be equal to 180 degrees according to the rules I mentioned. Therefore, this missing angle must be equal to 180 degrees minus beta. Because 180 degrees minus beta plus beta is 180 degrees. That is the sum of the opposite angles in a quadrilateral that is described by a circle. So if we found out that we have here two angles, this is angle beta, this angle is 180 degrees minus beta. The sum of those two angles is 180 degrees. Why? Because 180 degrees minus beta plus beta is 180 degrees. So we have here two one-sided interior angles, that the sum of those two angles is 180 degrees. And therefore, according to rule 18, there must be between two parallel lines. That is to say, QB is parallel to PM. So, I repeat quickly rule 18. According to rule 18, if the sum of one-sided interior angles is equal to 180 degrees, then they are located between two parallel lines. So in the drawing we have line A and line B. This is the red line C that intersects with those two lines A and B at those 2 points. And we know that alpha plus beta is equal to 180 degrees. Alpha and beta are two one-sided interior angles, and we know that the sum of those two one-sided interior angles is equal to 180 degrees. And therefore, according to this rule, whenever you have the sum of two one-sided interior angles that is equal to 180 degrees, then they must be between two parallel lines. That is to say, line A is parallel to line B. So we can actually implement rule 18 in our drawing. Why? Because in our drawing, we have those two one-sided interior angles, and the sum of those two one-sided interior angles is 180 degrees. Therefore, according to rule 18, they must be between two parallel lines. That is to say, QB is parallel to PM. Again, QB is parallel to PM according to rule 18. QB is parallel to PM according to rule 18. So in the next step, I'll copy again this semicircle with the diameter PM, and we'll continue to analyze this semicircle with the diameter PM. So actually, this is the semicircle with the diameter PM that I copied from the original drawing. Point O is the center of this semicircle. PQ equals to 10 units, MB equals to 10 units, and QB is the missing line segment that we are looking for in this question. It is equal to X, we have to find out the value of X. In the next step, we will join points O and Q together by side line. Point O is the center of the semicircle, point Q is the point of the semicircle itself, therefore Q is the radius of this semicircle, this is equals to 15 units in its length. Likewise, we join points O and B together by a straight line. Again, point OO is the center of this semicircle, point B is the point of the semicircle itself, therefore OB is also the radius of this semicircle, this is equals to 15 units in its length. We have already found out that QB is parallel to PM. According to Rule 18, QB is parallel to PM. QB is parallel to PM, and those two angles, that is to say angle OQB, and this angle, this is actually angle QOP, they are defined as alternating angles, and they are located between the parallel lines QB and PM. QB is parallel to PM, and therefore they are equal to each other according to Rule 15. So I repeat quickly Rule 15. According to Rule 15, alternating angles between parallel lines are equal to each other. In the drawing we have line A that is parallel to line B, and those two angles alpha and beta are defined as alternating angles. And because of the fact that those two angles alpha and beta are located between those two parallel lines A and B, they are equal to each other. That is to say, alpha equals to beta. So whenever you have alternating angles that are located between parallel lines, they must be equal to each other. So you can actually implement Rule 15 in our drawing. Why it goes in our drawing? As I already mentioned before, those two angles are defined as alternating angles, and they are located between the parallel lines QB and PM. QB is parallel to PM. And because of the fact that those two alternating angles are located between the parallel lines QB and PM, they must be equal to each other in their sizes. That is to say, this is again OQB, that is equal to this angle, that is actually QOP. They are equal to each other according to Rule 15, because they are alternating angles that are located between the parallel lines QB and PM, therefore they are equal to each other. So if we define one angle as alpha, then the other angle must be also equal to alpha, because they are equal to each other according to Rule 15. So in the next step, I will present to you the law of cosines, and we will implement the law of cosines in this green triangle, triangle POQ, and in this white triangle, triangle QOB. So I repeat quickly on the law of cosines. The law of cosines is true in any triangle. So actually, this is triangle ABC that could be any triangle. The length of line AB, or the length of side AB, is equal to A units. AC, this is side AC, and the length of this side AC is equal to B units. And this is side BC. The length of this side BC is equal to C units. This is angle theta. According to the law of cosines, this triangle ABC, that could be any triangle. Cosine theta equals to A squared plus B squared minus C squared over 2 times A times B. Repeat again. In this triangle ABC, that could be any triangle. Cosine theta equals to A squared plus B squared minus C squared over 2 times A times B. So we can actually implement the law of cosines in any triangle. So we'll implement the law of cosines in this green triangle, POQ. So I'll copy triangle POQ in a new page, and we'll implement the law of cosines in this green triangle. Here side OP of course equals to 15 units. It is the radius of the semicircle. Side OQ, side OM. This is side OM. That is also equals to 15 units in its length. It is the radius of this semicircle. QO also equals to 15 units in its length. So actually, this is the green triangle POQ. So the copy from this page. In this triangle POQ, this is angle alpha. According to the law of cosines, in this triangle POQ, this will be equation 1, cosine alpha equals to 15 square plus 15 square minus 10 square divided by 2 times 15 times 15. Repeat again. This triangle POQ, according to the law of cosines, cosine alpha equals to 15 square plus 15 square minus 10 square over 2 times 15 times 15. In the next step, I'll copy this white triangle QOB in the new page, and we'll implement the law of cosines in this white triangle QOB. So here, this is triangle QOB, just a copy from this page. In this triangle QOB, according to the law of cosines, this is angle alpha. According to the law of cosines, this will be equation 2. Cosine alpha equals to x squared plus 15 squared Actually, we have to talk on those two triangles. Okay, here cosine alpha equals to x squared plus 15 squared minus 15 squared over 2 times 15 times x. So this is the value of cosine alpha according to equation 2. And we already found out that according to equation 1, cosine alpha equals to 15 squared plus 15 squared minus 10 squared over 2 times 15 times 15. So we have two different equations for the value of cosine alpha. So in the next step we create equation 3 that states that cosine alpha according to equation 1 must be equal to cosine alpha according to equation 2. And again, according to equation 3, equation 3 states that cosine alpha according to equation 1 must be equal to cosine alpha according to equation 2. Okay? So, cosine alpha according to equation 1 equals to (15 squared plus 15 squared) minus 10 squared over 2 times 15 times 15, and it must be equal to cosine alpha according to equation 2. Cosine alpha according to equation 2 is equal to x squared plus 15 squared minus 15 squared divided by 2 times 15 times x. So here, this is equation 3. According to equation 3, cosine alpha according to equation 1 must be equal to cosine alpha according to equation 2. So here we have 2 times 15 in the denominator of this expression, and we have also 2 times 15 in the denominator of this expression. So 2 times 15 will get cancelled. Here we have 15 squared minus 15 squared, that is 0. So in total, in this side of this equation 3, we have only with x squared over x. X squared over x is x. So in this side of the equation, we have only with x. On the other side of the equation, we have 15 squared plus 15 squared minus 10 squared divided by 15. So in total we found out that according to equation 3, x is the line segment that we are looking for in this question, is equal to 15 squared plus 15 squared minus 10 squared over 15. So x equals to 15 squared. 15 squared is 225. So it is 225 plus 225 minus 10 squared is 100 divided by 15. So we found out that x is the length of line segment QB is equal to 225 plus 225 is 450, and 450 minus 100 is 350 divided by 15. So in total we found out that x equals to 350 over 15. Here we divide both the numerator and the denominator of this number by 5, and you get that 350 over 5 is 70, and 15 over 5 is 3. So in total we found out that x equals to 70 over 3 units in its length. X is QB. So the length of line segment QB is equal to x. It is equal to either 70 over 3 units in its length, or in terms of numbers, 70 over 3 is 23 and 3rd units in its length. That is the answer to the question. Repeat again, we found out that the length of this line segment QB is equal to x. It is equal either to 70 over 3 units. In terms of numbers, the length of line segment QB is equal to x is equal to 23 and 3rd units in its length. So finished the rest of the question. So in the next step, I'll summarize the lecture. I'll start with the first question, of course. In the first question, our mission is to find out the area of this circle that is described by this trapezoid ABCD. Trapezoid is a quadrilateral with one pair of parallel sides. So this trapezoid ABCD, side AD is parallel to side BC. So again, our mission is to find out the area of this circle that is described by trapezoid ABCD. In addition, we know that this is line segment AM, that is equal to A units in its length. This is line segment AMB, that is equal to B units in its length. Again, our mission is to find out the area of this circle. So first of all, we define the center of this circle. This point is point O. We define the point of tendency of tangent AD with this circle. This point is point P. And finally, we define the point of tendency of tangent BC with this circle. This point is point Q. Here, we can implement rule 2. According to rule 2, the lengths of two tangents from a common external point to a circle are equal. So if you focus on this common external point, point A, from this common external point, point A, we have two tangents to this circle, tangent AM and tangent AP. And according to rule 2, they are equal to each other. That is to say AM equals to AP. But AM is 8, according to what is given as the equation. Therefore, AP must be also equal to units in its length. Likewise, we focus on this common external point, point B. From this common external point, point B, we have two tangents to this circle, tangent BM and tangent BQ. And according to rule 2, they are equal to each other. That is to say, BM equals to BQ. But BM is B, according to what is given as the equation. Therefore, BQ must be also equal to B units in its length. And the next step, we join points O and Q together by a straight line. Point O is the center of the circle, point Q is the point of the circle itself, therefore OQ is the radius of this circle. We define the radius of this circle as x, so OQ equals to x. And because of the fact that the radius of Q that is equal to x, the radius of Q is 1 to point Q, that is the point of tendency of tangent BC with this circle, and whenever your radius that is 1 to the point of tendency, then tangent BC will be perpendicular to the radius QO. If BC is perpendicular to QO, then this angle must be equal to 90 degrees, and this angle also must be equal to 90 degrees according to rule 1. Likewise, we join points O and P together by a straight line. OP is the radius of this area that is equal to x. And because of the fact that the radius of P is equal to x, the radius of P is 1 to point P, that is the point of tendency of tangent AD with this circle. Whenever you have radius that is 1 to the point of tendency, then tangent AD will be perpendicular to the radius PO. If AD is perpendicular to PO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. In the next step, we did the construction, that is to say, from this point A, we do perpendicular on BC. Again, from point A, we do perpendicular on BC. So actually, this angle equals to 90 degrees, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We find the touching point of the perpendicular from point A and BC. This point is point 10. By doing this construction, we can do those two angles. Those two angles are defined as one-sided interangles, and they are located between the parallel lines AD and BC. AD is parallel to BC because of the fact that ABCD is a trapezoid. So those two one-sided interangles are located between the parallel lines AD and BC, and therefore, according to Rule 17, the sum of two one-sided interangles that are located between parallel lines must be equal to 180 degrees. So, according to Rule 17, the size of this angle plus this missing angle, in total, it must be equal to 180 degrees. But this angle equals to 90 degrees according to construction. So 90 degrees plus this missing angle, in total, the sum of those two angles must be equal to 180 degrees. Therefore, this missing angle must be equal to 90 degrees in its size. Okay. In the next step, we did another construction, that is to say, from this point O, that is the center of this circle, we do perpendicular on AN. So, again, from point O, we do perpendicular on AN. So, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and AN. This point is point T. By doing this construction, we created the small polynomial APOT. Inside this small polynomial APOT, we have 1, 2, 3 angles. The sum of 3 angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle, in total must be equal to 360 degrees according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. Likewise, inside this quadrilateral TOQN, we have 1, 2, 3 angles. The sum of 3 angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle, in total must be equal to 360 degrees according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So in total, we have found out that the big angle POQ, the size of the big angle POQ is 90 degrees plus 90 degrees, that is 180 degrees. Repeat again. The size of the big angle POQ is 180 degrees. And we know that any angle that is equal to 180 degrees in its size, it is defined as a straight line. So line segment POQ is a straight line. Line segment POQ is a straight line. If POQ is a straight line, then PQ is also a straight line. Okay, PQ is also a straight line. So if you found out shape APQN consists of 4 sides. Again, shape APQN consists of 4 sides. 1, 2, 3, 4. Okay, repeat again. Shape APQN consists of 4 sides. And therefore, shape APQN is a quadrangle because it consists of 4 sides. Shape APQN is a quadrangle. Inside quadrangle APQN, we have 4 right angles. And according to rule 5, any quadrangle that has 4 right angles must be a rectangle plus a square. So we need to quadrangle APQN as a rectangle because it has 4 right angles. Okay? But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle APQN, side AB must be equal to the opposite side QN. But AP is A, therefore QN must be also equal to A in its length. Likewise, according to the same rule, in the same rectangle APQN, side PQ must be equal to the opposite side AN. But PQ is x plus x, that is 2x, therefore the opposite side AN must be also equal to 2x units in its length. Okay, what is the length of the missing line segment NB? NB equals to NQ, NB equals to BQ minus NQ. Again, NB equals to BQ minus NQ. So NB equals to BQ, that is B, minus NQ, that is A. So in total, BN equals to B minus A units in its length. BN equals to B minus A units in its length. So in the next step, I copied the right triangle A and B in a new page and implemented the Pythagoras theorem in this right triangle, triangle A and B. According to the Pythagoras theorem, in the right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. This is the right triangle A and B that are coming from the original drawing. Here AB equals to A plus B. Therefore, AB equals to A plus B units in its length. In this right triangle A and B, AB square equals to AN square plus BN square. Again, AB square equals to AN square plus BN square. AB is A plus B, therefore AB square is A plus B square, and it is equal to AN square. AN is 2x, therefore AN square is 2x squared, that is 4x squared, plus BN square. BN is B minus A, therefore BN square is B minus A square. So in total, we should find out that A plus B square equals to 4x squared plus BN square. A plus B square equals to 4x squared plus B minus A square. We open the brackets on both sides of this equation and find out that A plus B square equals to A square plus B square plus 2 times A times B. And it is equal to 4x square plus B minus A square. B minus A square equals to B square plus A square minus 2 times A times B. Here we have A square on both sides of the equation, so A square will get cancelled. And you also have B square on both sides of the equation, so B square also will get cancelled. After cancel those two expressions, inside of the equation we have to leave 2AB. On the other side of the equation we have 4x squared minus 2AB. So in total we found out the 2AB equals to 4x squared minus 2AB. We added 2AB to this equation and finally found out that 2AB plus 2AB is 4AB, so 4AB equals to 4x squared. Here we divided this equation by 4 and finally found out that 4AB over 4 is AB and 4x squared over 4 is x squared. So in total we found out that x squared equals to AB. Our mission is to find out the area of this circle. Actually we know that the area of any circle equals to pi times the radius of the circle squared. And therefore the area of this circle must be equal to pi times the radius of this circle squared. The radius of this circle is x, therefore the radius squared is x squared. So in total we found out the area of our circle must be equal to pi x squared. What x squared is AB. Therefore we substitute x squared here by AB. And finally found out that in total the area of the circle must be equal to pi AB square units. Again, the area of this circle must be equal to pi times AB square units. We finish with the first question. In the next step I present the second question and we solve the second question of this lecture. Our mission in the second question is to find out the length of this line segment qubit is equal to x. We have to find out the value of x. So in the original drawing we had a semicircle. and this is called AP, this is equal to 10 units in its length. This is called PQ, this is also equal to 10 units in its length. AB, this is the diameter of this semicircle, is equal to 30 units in its length. This is called QB, is equal to X, and we have to find out the value of code QB is equal to X. We have to find out the value of X. So the first step, we define the center of this semicircle. This point is point O. Because of the fact that the diameter AB of this semicircle is 30, therefore the radius must be equal to half of it. That is to say, the radius must be equal to 30 over 2, that is 15. So the radius of this semicircle is 15. Point O is the center of the semicircle, point A is the point on the semicircle itself, therefore OA is the radius of this semicircle, that is 15. Likewise, OB is also the radius of the semicircle, that is 15. We join points on P together by side line. OP is also the radius of the semicircle, that is 15. In the next step, we completed this semicircle to a circle, and we extended the radius PO until it touches the circle at this point. We define the touching point of the extended radius PO with this circle. This point is point M. In the next step, we join points M and P together by straight line. Those angles are defined as vertex angles, and we know that vertex angles are equal to each other. So if this is angle theta, that this angle must be also equal to theta because they are equal to each other according to the rule that I mentioned. In the next step, we prove that the right angle P, it is not right angle, triangle POA can go into this triangle BOM. So all those two triangles can go into each other. First of all, PO equals to OM. They are both the radii of the circle, therefore they are equal to each other. In addition, those two angles are vertex angles. We know that vertex angles are equal to each other. So those two angles are equal to each other. And finally, side AO of triangle AOP is equal to side OB of triangle OMB. They are both the radii of the circle, therefore they are equal to each other. So if you found out that those two triangles can go into each other according to side angle side rule. We have those two sides and the angle that is included between those two sides in triangle POA are correspondingly equal to those two sides and the angle that is included between those two sides in triangle BOM. Therefore, those two triangles can go into each other according to side angle side rule. And from the fact that they can go into each other, we derive that side PA equals to side VM. According to the rule, the corresponding sides that can go into triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding sides PA and VM must be also equal to each other. But PA is 10. So we can write here that PA equals to 10, and from this equation 10 equals to AP equals to MB, we derive that MB also equals to 10 units in its length. This is 97 MB, that is equal to 10 units in its length. We know that chord PM, this is chord PM, passes through point O, that is the center of this circle, and we know that any chord that passes through the center of the circle must be the diameter of the circle. So PM is the diameter of this circle. So in the next step, we copy this semicircle with the diameter PM and we analyze this semicircle. So okay, this is the semicircle with the diameter PM that are going from the original drawing. Point O is the center of this semicircle. And in the next step, we know that we actually found out that we know that QP equals to 10 units in its length and BM also equals to 10 units in its length. So those two line segments are equal to each other in their lengths. So in the next step, we extended those two line segments that are equal to each other in their lengths until they intersect with each other at point E. And because of the fact that those two line segments are equal to each other, when you extend two line segments that are equal to each other in their lengths until they intersect with each other, the new line segments must be also equal to each other. That is to say, the new line segments are EP and EM. So EP must be also equal to EM. So EP must be also equal to EM. So in triangle PEM, side EP equals to side EM, therefore this triangle is an isosceles triangle. And we have the rule that in front of equal sides in the triangle there are equal angles. So in front of this side EP we have this angle, in front of this side EM we have this angle. and because of the fact that those two angles are located in front of those two equal sides, they must be also equal to each other in their sizes. So if the size of this angle is better, then the size of this angle must be also equal to each other, because they must be equal to each other according to the rule that I mentioned. In the next step, we completed this semicircle to a circle. So in the drawing we have quadrangle QP and B. Quadrangle QP and B is inscribed by this circle, and we have the rule that says that any quadrangle that is inscribed by a circle, the sum of its two opposite angles is equal to 180 degrees. That is to say, in this triangle QP and B that is inscribed by this circle, the sum of those two angles that are defined as opposite angles must be equal to 180 degrees. But this angle equals to beta. So beta plus this missing angle, total the sum of those two angles must be equal to 180 degrees according to the rule that I mentioned. Therefore, this missing angle must be equal to 180 degrees minus beta. Why? Because 180 degrees minus beta plus beta is 180 degrees. That is the sum of the opposite angles in a quadrangle that is described by a circle. Therefore, this missing angle must be also equal to 180 degrees minus beta. Likewise, those are two opposite angles, and the sum of those two opposite angles must be equal to 180 degrees. But this is angle beta, therefore this missing angle must be also must be equal to 180 degrees minus beta. But why? Because 180 degrees minus beta plus beta is 180 degrees. That is the sum of the opposite angles in a quadrangle that is described by a circle. So in total, if we found out those two angles, we know that they are defined as one-sided into angles, and the sum of those two angles is 180 degrees minus beta plus beta is 180 degrees. So we have the sum of two one-sided into angles is equal to 180 degrees. And therefore, according to rule 18, those two angles must be located between parallel lines. That is to say, QB must be parallel to PM. Again, QB must be parallel to PM according to rule 18. In the next step, I complete again the semicircle with the diameter PM, and we continue to analyze this semicircle. So actually, this is the semicircle. Let's over here. PQ equals to 10 units in step, BM also equals to 10 units in step. Point O is the center of the semicircle, OM is the radius, that's 15. OP is also the radius, OQ is the radius, and OB is the radius, and OQ is the radius. They are all equal to 15 units in their lengths. QB is the missing side, is equal to X. This is the last segment that we are looking for with this question. We have already found out that according to rule 18, QB is parallel to PM. Those two angles are defined as alternating angles, and they are located between the parallel lines QB and PM. And therefore, according to rule 15, they must be equal to each other in their sizes. That's to say, according to rule 15, alternating angles between parallel lines are equal to each other. So those two alternating angles that are located between the parallel lines QB and PM must be equal to each other. So if we define the size of this angle as alpha, then this angle must be also equal to alpha, because they are equal to each other according to rule 15. In the next step, I presented to you the law of cosines, and implemented the law of cosines in this red triangle PQO, and in this white triangle, triangle OQB. So what is the law of cosines? The law of cosines is shown in any triangle. This is triangle ABC that could be any triangle. Side AB equals to A unit in step, side AC equals to B unit in step, side BC equals to C unit in step. This is angle theta. In this triangle ABC that could be any triangle, cosine theta equals to A square plus B square minus C square over 2 times A times B. So we implemented the law of cosines in the green triangle. So I call it the green triangle. This is the green triangle that I call it from the previous page. The green triangle QPO. This green triangle QPO, cosine alpha equals to 15 square plus 15 square minus 10 square over 2 times 15 times 15. This is equation 1. The next step, I copied triangle QBO in this new pad and implemented the law of cosines in this triangle QBO. According to the law of cosines in this triangle QBO, cosine alpha, this is angle alpha, cosine alpha equals to x squared plus 15 squared minus 15 squared over 2 times x times 15. So this is equation 2. So we have two equations for cosine alpha, equation 2 and equation 1. In the next step, we added equation 3 that says that cosine alpha according to equation 1 must be equal to cosine alpha according to equation 2. So cosine alpha according to equation 1 is equal to 15 squared plus 15 squared minus 10 squared over 2 times 15 times 15. And it must be equal to cosine alpha according to equation 2. Cosine alpha according to equation 2 equals to x squared plus 15 squared minus 15 squared over 2 times 15 times x. So we have in the denominator of those two expressions 2 times 15 on both sides of the expression. So 2 times 15 will get cancelled. Here we have 15 squared minus 15 squared, that is 0. So total we left here with x squared over x, that is x. This side of the equation we left with 15 squared plus 15 squared minus 10 squared over 15. So in total, according to equation 3, I should find out that x equals to 15 squared plus 15 squared minus 10 squared over 15. 15 squared is 225. Again, 15 squared is 225 plus 10 squared, that is 100 over 15. So x equals to 225 plus 225 is 450. 450 minus 100 is 350 over 15. So total, I should find out that x equals to 350 over 15. Here we divided both the numerator and the denominator of this number by 5. And finally found out that 350 over 5 is 70. 15 over 5 is 3. So in total, I should find out that QB, therefore for find 7 QB is equal to x. It is equal to either 70 over 3 units. In terms of numbers, it is equal to 23 and 3 units in its length. I repeat again, I should find out that the length of this 97 QB is equal to x. It is equal to either 70 over 3 units in its length. In terms of numbers, 97 qubit is equal to x. It is equal to 23 and 3 units in its length. Okay, thank you very much.